This is a second topic related to the first in the sense that we're talking about signals, but it really allows us to move from an analog representation to a digital representation of a signal. So, what does that mean? So this simplest image of all is the one you see in front of you now, in which we see the green line, which shows an analog representation of, in this case, a simple sinusoidal type function. And the blue steps are one representation of the digital version of that. And this representation, this picture, contains both aspects of a digital capturing of a signal that we have to take into account when we're moving from this analog to digital space. And of course, we do this all the time. All the videos we watch, the music we listen to, it lives in digital form on our devices. And then it gets converted into analog form to make a picture or make a sound that we hear through speakers or our headphones. So this conversion back and forth is something that's happening all around us all the time. We would never think anymore to capture a signal in anything but digital form. In a biomedical engineering situation, whether that's an ECG or a blood pressure signal, anytime we have a time-varying signal, we capture it in digital form. So we need to know something about that capturing process. Not so much the electronics and details, that's a whole other chapter, but the fundamental characteristics and criteria that we use to understand how we convert between the two. So the idea here is to understand how we get from the green line, which is a smooth signal with infinitesimal resolution, both in time and in amplitude, to that blue signal, which has discrete sampling points in time and discrete sampling levels in amplitude space. Okay, so let's dive into this. So there are two different aspects here that we can consider, and you see them here in this display, and we'll talk about each separately. One is the sample rate, as in the temporal sampling, the sampling with time. So the red balls represent an instantaneous value that we captured from a signal that you can already put together just by looking at it as some, again, sort of sinusoid type function. But each time we sample in time, we get one value. We get a single value. We get the value of where the ball is, the amplitude of the height of that ball above or below the zero line. That's what we get when we sample in digital domain. And there's a frequency with which we do it, and that's called the sample rate. The other side is the level of discrete amplitudes that we collect. Because we don't collect any amplitude, we decide for every sampling we do, is that a 1.2 or a 1.4? Or is it a 1 or a 2? Or is it a 1 or a 6? Depending on the resolution between our sample amplitudes. And that's the resolution, or what we call the bit depth in the digital scenario. And we'll get to both of those. So again, both of them are arguably orthogonal components of this whole sampling question. So let's start with the temporal aspect. Now, one of the things you've read about in the textbook, hopefully, is this notion of minimal sampling rates. It turns out that there's some wonderful information theory that was developed a century ago to understand how we can capture, and more importantly, how we can reconstruct from discrete sampled signals. So if we sample a signal very frequently, then it's not hard to imagine that we can reconstruct it pretty easily, right? There's an intuition for that. What is less intuitive is that the frequency we need to sample with is not really very high. So if we look at this example here, this is a situation we have two full cycles and something like 20 maybe samples for each one of the cycles. There's probably 10 samples in each one of those positive and negative halves. So we have a sampling rate that's twice as frequent as we need, because we know we only need 2 samples per original highest frequency component that we have in our signal. That's what the Nyquist criterion actually says. And again, read about that in the textbook. It's important that you at least understand what it says. What does it mean? Well, let's look at another case. Let's look at a situation where, again, the red signal is the analog signal we're trying to sample, and the black dots show where we've sampled in time. We're not going to worry about the analog or the amplitude discretization at this point. So we've perfectly measured the amplitude at those points where the black dots are. And then we have to reconstruct those black dots. We have to connect them again in such a way to reconstruct the signal. Now it turns out that if we have, in this case, a sampling at 3/4 or 0.75 of the minimum amount, the minimal level of sampling we need, that when we reconstruct, we get that dashed black line. And the dashed black line is clearly not the original red line. And we see we actually have a reduced false sinusoid is what we call it. So we have a reduced frequency. It may still look like a sinusoid. That has something to do with the reconstruction process. But the point is that we will not be able to ever reconstruct that signal, no matter what tricks we use, if we don't sample at a high enough frequency, and that frequency is the Nyquist frequency, which again is at least twice the highest frequency component in the signal we're trying to capture. These are simple signals to capture because they're sinusoids, so they only have one frequency. And we just need to sample it twice that frequency in order to reconstruct it. So we'll look again. Here's that case where we have exactly the Nyquist frequency. So here you see, if you look carefully, you'll see the black dots. There's 2 black dots for every cycle. There's actually one at the beginning and one at the end, but the end is the same as the beginning. So there's really 2 sample points within a single cycle of that red sinusoid. And there again, if we reconstruct, we don't quite have enough information to reconstruct properly. Instead, we get this lower amplitude signal that doesn't truly reconstruct what we started with. So again, you see the amplitude distortion is the big one, and it's also phase shifted from the original signal. So we need a little bit more information, as it turns out. So we need to sample slightly higher than the minimal Nyquist frequency, the highest frequency component in the signal we want to sample. We have to sample a little bit higher than that. And what you see below now in this other reconstruction is a correct reconstruction where we sample a little bit higher. So if you look at the black dots, they're a little more frequent than 2 per 1 cycle of the original signal. And that's how sampling in time works. So again, we can have sampling at the exact Nyquist frequency, and it doesn't work if we sample, in this case, at 25% higher than the original or than the required minimum. We get a proper reconstruction. And that's part of the magic that we get with sampling. And this is why all these considerations were so fundamental. So another aspect that we won't get into too deeply, but you should appreciate, is that when we sample, we get sort of a lollipop diagram, you can call it. All we get is a series of amplitudes, and we have to then connect them. So we can correct them, or we can connect them in a stair-step manner, in which we literally draw a flat segment between our measurement points. So we pick a measurement point, we move over in space until we get the next measurement point, then we jump to that one and we move over in space. And you've seen this kind of image. If you zoom in on an image, which again is a signal, then you've seen this sort of stair-step pattern. If you zoom in on a recorded signal of music, eventually you'll see something like that. But part of the problem is that we haven't actually reconstructed it properly. So the reconstruction of a sampled digital signal is not by connecting the dots in a straight line sort of way. It's much more complicated than that. It involves each one of those points being the center of its own function, and that function being a sine x over x function, and then adding up all those contributions. Now that sounds complicated. It is kind of complicated. There are ways that this is implemented in hardware for us. A really good implementation in hardware is a relatively expensive piece of equipment. A really good digital to analog converter can easily cost you $100. The cheap ones that we put up with in our portable devices don't actually do that good a job. And we sort of make up for it by sampling higher than we actually need to. So there are these engineering compromises we don't have time to get into in detail. But we need to at least appreciate that reconstruction of sampled signals is not just connecting the dots, and certainly not connecting them in a stair-step manner. That will not give us an accurate reconstruction. It takes more than that to get the actual sampling. And again, we make up for that, or we cut corners on the reconstruction by sampling slightly higher than we need to, because then the reconstruction becomes easier. And this is the inevitable engineering trade-off that we certainly see again and again in engineering. And so you will see that practically, if you want to, for example, have frequencies up to 100 hertz, that's a relevant frequency range when we're trying to capture an electrocardiogram, for example, that the practical advice will be not to sample just at 200 hertz, twice the base frequency, but to sample at 500 hertz. And that will give us oversampling, and with that oversampling, it's a little bit easier to reconstruct the signal and be sure that we get all the information up to that 100 hertz that we thought was initially of interest. So these are tricks and games that we play to deal with incomplete sampling. So that's the sample part, that's the time part. Now let's talk about the resolution or bit depth. So this is the level of discrete amplitudes that we use to capture a signal. Remember the lollipops. So before, the lollipop in principle could have any level. But now we're saying, no, this is a digital signal. It has to be stored as a number, and digital numbers are stored with discrete numbers of bits, discrete levels that come from that. So we can picture it here with this diagram. So here is a signal. Again, in red is the original signal. The blue dots are the lollipops. And what we see here is we have a 0 level, and then 7 levels above 0 and 8 levels below 0. There's an asymmetry here we don't need to worry about. It comes out of the way we represent signals in digital form. 0 takes away one of the positive values. So anyway, we have these discrete levels, and for every point in time, we have a vertical line that tells us where we're sampling in time. And then for each case, we have to decide whether we sample at, for example, that point at the top of the initial peak there, do we sample and call that a 7, or do we call that a 6? And so we interpolate, we approximate, we round. So we say, well, that red line looks like it's a little closer to 7 at that point. I'm going to take 7 and give it the value of 7, because I only have these 16 values with which to encode my number, the number that I record when I convert this analog signal into digital form. So this is a 16 sample rendering of the situation, and I get 16 samples with 4 bits. That's the conversion. Every bit is an additional yes, no, or an additional 0, 1, and if I keep adding more and more bits, I add more and more overall ultimate levels. And so the number of bits I have determines the level of resolution I have in my amplitude space. And if I don't include enough of those levels, then I create an error, of course, because when I reconstruct the signal, as we see in this case, when I reconstruct at the green levels, then I see that I'm not at the same amplitude. Even though the shape is relatively similar, I'm not perfectly reconstructing the shape of the original red signal. And sometimes we overestimate it, sometimes I underestimate it. You can see cases of both in this figure. And that leads to noise, leads to error. And it's called quantization noise, is what we call it. And here you see a rendering of the original signal in green, the quantized or reconstructed signal after I've used discrete amplitude levels in yellow, and then that red signal at the bottom, that's the quantization noise. And that noise we hear if it's an audio signal, or we see if it's an ECG. So these are differences that may or may not matter. Here we come back also to the notion of signal to noise and that signal to noise ratio. And as long as the signal is larger than the quantization noise, then we live with that. We accept that as the inevitable consequences of saving space in the storage, because I'm motivated to use the smallest number of bits I need, because every bit or every byte or every number I store takes up space in my digital storage system. And so there's no compelling reason to use any more bits than necessary for the level of quality that we want in the captured version of the signal, which again will have error. Every discretized signal has a certain amount of error, and we have to decide how much error is acceptable. And we can capture this bit depth as the number of bits that we have. We can talk about the smallest bit being the smallest step size. So the number of bits dictates how many steps we have, and the smallest of those bits, the fluctuation of that, determines the smallest step size we have. We can convert that into ratios of the number of bits that we have versus the 1 bit that is our smallest size. We can take ratios of that and turn those into dB numbers, which is a number that is very relevant. It's a ratio. Any dB number is just a ratio. It's a logarithmic form of that ratio. So you'll come across this in engineering. And it gives us a notion of, in this case, the dynamic range, the number of values between the largest and the smallest, let's say, amplitude that we can capture in a sound signal, the loudest sound versus the smallest sound that we can capture. And we can directly correlate the dynamic range we can achieve to the bit depth that we determine. What you see here is a table with the number of bits, the number of discrete values that come from those number of bits, and then the dynamic range expressed in dB. And again, you'll see these numbers when you look at audio recordings, for example. And we can see that as we add more bits, we add more values, we add more dynamic range, everything is good, except each one of those additional bits means we have to store it. And so we make compromise decisions between how much storage space we have and how much resolution in amplitude or dynamic range, as in the difference between the loudest and the smallest sound that we're going to actually capture in our recording, if it's a sound recording. And here we see an example of the same signal rendered, in the one case with 3-bit resolution, which is the blue line, and you can see how really very crude that rendering is, compared to 16-bit resolution, which is essentially perfect. You can't tell the difference between the original signal and the 16-bit resolved signal. And that tends to be a good rule of thumb, that at those resolutions of 16-bit or so, we really have an amazing dynamic range and a resolution that is good enough for almost anything in practice that we'd ever want to do. And so you will see in many devices that arise in biomedical engineering that a 16-bit resolution has become the current standard. Storage space is cheaper than it once was. We're less motivated to save that space and more motivated to capture a better quality signal. So 16 bits has become a bit of a standard now, across many domains. So the noise levels can be hard to predict. They will vary with the nature of the signals. Here we see an example of an original signal in blue, the quantized signal in red over top of it, and then the noise level. And we see that the noise down at the bottom there is not constant with time, even over the single cycle here. So this quantization noise can become a problem because it's not a consistent level of noise even. So it can come and go depending on where we are in the signal itself. So these are all features that we need to think about when we're actually making recordings and building devices. So they're very practical considerations. Now, one practical aspect that you've all probably encounter almost every day is music, is listening to music. And so there are standards, whether you've acknowledged them or not, there are standards that exist for temporal sampling rate, to go back to that first topic, as well as the bit depth for different types of recording. And the audio industry decided that to make compact discs, and that was the medium that first came out that replaced long playing records and magnetic tapes, it was really the first truly digital form of recording. Vinyl recordings or analog recordings. Tapes, the original tapes, the cassette tapes we have, those are analog recordings. They don't work through digital means. So CD or compact disc was the first digital form of recording in widespread use. And for that, the industry decided that 44 kilohertz was a good frequency to pick, and they said 16 bits. So again, the 16-bit was already common there. Why 44 kilohertz, you might well ask? That also derives from our physiology, because it turns out that a normal person or a person with normal hearing, especially a young person whose hearing is still fully intact and has a sort of wide flexibility, that person can typically comprehend or sense through their ears frequencies in the range of approximately 20 to 20,000 hertz. That's the range of frequencies that a young person will be able to hear and discern as sound. They may not distinguish every frequency, of course, but they can hear some sound at all those frequencies. And so if we think about the Nyquist sampling criterion, that's sampling at twice the frequency of the highest frequency component of interest, and we think the highest component of interest is 20 kilohertz, then 44 makes a great deal of sense. 44 kilohertz is a little more than twice the highest frequency that we think a person is likely to be able to hear. So that made a great deal of sense. Why 44.1? I don't know. Be a great question to dig into in terms of the history of this technology. But that's the frequency that CDs are collected at. Now things have evolved since then. There's been other forms of digital recording. The frequencies have changed. There's recording of digital audio tapes. They tend to run at higher frequencies at 48 kilohertz. And then we get into a standard that is rarely used of double the normal CD frequency. And then we get into DVD frequency where we have 96 kilohertz. And then finally, the DVD audio, top DVD audio quality, which we'll find anywhere, and that's in the range of 192 kilohertz. And when you think about it, this is massive oversampling, of course. And I said before, sometimes oversampling was good. It allowed you to cut some corners on the reconstruction, and that's what the benefits are. But in practice, this range of, say, 48, maybe 96 is easily within a reasonable range, easily covers the frequencies of interest. Now, bit depth also has gone up. I told you 16-bit achieves a great deal of resolution and is adequate for many situations. For, again, reasons of just overkill almost, we now see 24-bit very commonly in digital recordings. So literally on your phone or in a digital computer. When recording sound, you'll see these kind of frequencies. These are not the values you'd see recording a biological signal necessarily from other origins. They would be adjusted and adapted with these same compromises in mind to find what is the best trade-off between reconstruction or resolution needed to capture the information that's essential for a clinical diagnosis and the storage space or the technical overhead and required in the hardware to capture that. So just to put things in context, if you, I don't know, go home and talk to your parents, maybe they have small cassettes around. That was an analog modality, as I said, but we can convert that signal quality or the signal to noise ratio into its digital equivalent. And the best case we can hope for of a cassette tape like this historic item, would be something the equivalent of 9 bits of resolution. That's depth resolution. More typically be in the range of 5 to 6 bits. Tempo resolution doesn't matter so much here because it's analog. So the analog recording is continuous. And so we have very, very high sampling frequencies, or the equivalent of high sampling frequencies, because it is analog. But the functional depth of the recording, the resolution of the amplitude, is actually very modest. It was not spectacular. Now, I used to work in studios years ago, and there we had very high quality tapes, much more expensive, big wide tapes, and there the best case we ever got was 13 bits, which you'll remember is still nothing close to what we have in everyday devices around us. You have devices in your possession that have higher resolution than that. And again, these are still analog recordings. And then, to put it in context, a typical iPhone 6, not even typical anymore, it's an old iPhone 6, that had a 16-bit resolution and 48 kilohertz in its microphone of sampling rate. So we have amazing capabilities in our pockets, literally, brought about by cheap storage and very efficient and cheap electronics to perform these steps of both the analog to digital conversion and the digital to analog reconstruction. And so the mechanics of that, again, are something that you can get into if you're interested. There's certainly lots of fascinating electronics there. So that's the practical considerations that, at least an introduction to them, that come up in our world. So it's very common for a biomedical engineer to be brought in on a recording situation and have to design and build a recording system to capture that. We just finished building one in our lab. And so this is not strange and unusual requirement. Every signal that exists coming from the body has become something we wish to record, whether it's on a very expensive medical device or something as simple as the watches and Fitbits and other devices we wear to capture our heart rates and our heart signals. So these considerations apply to all these devices. And so hopefully you've gained a little bit of insight into how they work and what the various terminologies mean, and can at least start your deeper reading into what they all mean. So thanks for your attention, and we'll see you in the discussion section.